right, let's take a look at this simple harmonic motion problem. I like this one because it's fairly comprehensive and a lot of different scenarios can kind of fit into this general scenario here. So this is a mass spring system. The interface is frictionless between the mass and the substrate that's beneath it there. And we're told a couple of really important things off the bat here on the first line. This up here, we're told that let t equals 0 and x equals s over 2. So that's important. That's telling us that it's not up to us where to start the clock, right? That basically what this is about is that basically the phase shift or phase constant is set by the problem, the scenario here. That's not always the case. We've seen other scenarios where we're just given an oscillating thing and it's totally up to us to figure out what the coordinate system looks like and when we're going to let time equal 0 and all that business. But here, this is set up for us. So we'll walk into this. So time equals 0 when x equals s over 2. And we're also told that the amplitude equals 2s. So it's kind of an interesting problem. The clock doesn't start at a super convenient spot, right? The clock doesn't start at x equals 0 or x equal a, but it doesn't start at a super random spot either, right? It's a very well defined place here that when x equals positive s over 2, that's the time that we start the clock. Okay. So we have a really good idea of what this thing's doing. Obviously, it's oscillating with an amplitude 2s, and we know when the clock started. We're given k prime, m, and s, and we're asked to determine a whole bunch of stuff here, actually. But we'll start out by just looking at the angular velocity. So we're asked to find the angular velocity. So let's start there. And you know, I understand that you could be like, well, I could just look it up in the book because the book gives me a really cute little equation for a mass spring system, and that's true. But I would not be doing my job if we weren't um, going to look at how to derive that. So one of the really important things, this is especially true for mechanical engineering students, but one of the important things here is to know how to derive the angular frequency for an oscillating system. That's one of the things that you want to learn from this section here on simple harmonic motion. So that's why I keep taking you through it. If you keep wondering, why does she keep doing this when we could just look up the equation? That's why. So part A asks us for the angular velocity of the system, and I need to just start out with my equation of motion for the system. So with a simple harmonic motion problem, that's always where we start. And well, there are different ways we can write it, as you've seen when we've done these, but the most common equation is just a cosine omega t plus phi. You've seen problems before where we've used the sine function instead. But I think I'll go ahead and stay with cosine here. So there is my equation of motion, and then I can, from that, write my velocity equation, right, which is the first derivative of this equation here, negative a sine omega t plus phi, and then, of course, my acceleration equation, negative a, oh, I forgot an omega up there. Let's fix that real quick. That omega is important. Negative a omega. So we have negative a omega squared here, cosine omega t plus phi. Okay, and then we notice, as we always do with simple harmonic motion, this is the hallmark of simple harmonic motion, that the acceleration function is equal to a negative constant, in this case that's omega squared, times the displacement function or position function. So, and I have hats on all these guys for a reason. These are vectors, right? The signs matter. So if I have a positively directed, and here I have this positive, so let me put a sign convention on this here, positive x to the right. If I have a if I have a positive velocity, that tells me the velocity is rightward directed. If I have a negative velocity, that tells me for this problem it's leftward directed. And of course, that depends on your sign convention. But for this particular sign convention, the way I have it drawn, notice that we're told that let t equal 0 and x equal positive s over 2. And I have that drawn to the right, so rightward is implicitly positive, we can make it explicit with our sign convention. All right. Um, to take this relationship right here, and we can write that in a magnitude form. In a magnitude form, that tells me that the magnitude of my acceleration is equal to omega squared times the magnitude of displacement. Okay? So, and this is displacement from equilibrium. So we can, that's why I sometimes say displacement, and sometimes I'll say position, because it's displacement working as always measured with respect to x equals 0 for this application. So a lot of times students will get confused about the move from the to this magnitude expression. And what I say is that we do this actually all the time in force analysis. We use magnitude expressions there. So go back and look at that. This isn't all that different from what we do there. All right. So now I need to draw a free body diagram for my situation. And I'll go ahead and draw a free body diagram for just for the position that is shown in the diagram. For simple harmonic motion, the free body diagram changes, right? Depending on where you are, if you're on the right or left of the equilibrium, say. But for this particular one, I'm just going to use the snapshot in my diagram. So I'll draw my free body diagram here for the block. So let me be clear. This is for the block. And what does that look like? There's a normal force. The block has weight. And then there's a spring force that's pulling the block to the left, right? Correct? If I displace the block to the right, the spring force wants to restore. That's a restoring force. So that force is going to be directed to the left. What is the magnitude of that force? K prime x. Okay. So if I apply, and I have rightward positive here, if I apply second law, what do I get here? Negative K prime x is equal to 3m times negative a, right? Because I know that my acceleration is also to the left since I have obviously a net force to the left. I can solve this equation for x. X is equal to 3m a over k prime. And then I know here, I'm going to go back to this magnitude equation that I did, that I found right there. And I know that I can say acceleration is equal to omega squared, now times this expression for x, 3m a over k prime, and then solve for omega squared, k prime over 3m, and then of course that tells me that omega is root k prime over 3m. So I understand that you might be saying, well, this isn't a surprise. This is just the equation I could have looked up, and that's true. But it's really important to know how to derive that equation and to feel comfortable. And all of you have the math to do this. This is just doing some um, derivatives, single derivatives, right, with respect to time, free body diagram, and a little bit of algebra. All right, let's move on to part B. So part B asks us here for the phase constant. And remember, that the phase constant, the way I want you to think about this conceptually is it's that phi, right, in our equation, is all that that's about really is about reflecting where the clock starts. That's it. Remember that if for the cosine function, if you set t equals 0 equal to a every time, think about that, right? That maximum value, then phi would be equal to 0, right? If you're using the sine function and you start the clock when x equals 0, then phi is 0 for that function. So it's really just, and the behavior is all completely the same, right? The system would behave the same. So this is really just about starting the clock. So in this case, we're told when the clock starts that t equals 0 when x equal negative s, right? And we're given the amplitude. So we need to solve for phi. I'm going to start with my general equation, omega t plus phi here. And then I'll go ahead and sub in what I have, and this is a vector equation. So what I'm given is that in place for x, I'll put positive s over 2. is equal to amplitude is equal to 2s. We were given that in this equation, right? Cosine. Now, we're told that t equals 0, so that's going to be 0 for this term, when x equal s over 2. So that's why I put 0 in for the omega t term, right? Because this right up here, let t equal 0 and x equals s over 2. All right, so now I have this equation, and I can then use this to solve for what I need to solve for here. Then I've got, what do I have? Cosine phi is equal to 1 over 4. And of course, then phi will be equal to arc cosine 1/4. All right, so that is my phase constant for this problem. So don't let it be really mysterious. Remember, it's just about the initial conditions. And when you're not given the initial conditions, choose something convenient. And when you are given the initial conditions, it's the initial conditions that you can use in order to solve for phi. And notice that I did this for position because we were told what the position was. But I could do the same thing to solve for the phase constant in one of these other places too, right? I could do that. Okay. So that's part B. Part C asks for a free body diagram when the block is at x equal negative s. All right, so that's a different free body diagram than the one that we just drew, right? Because the one that we had drawn previously was for the block when it was to the right of equilibrium. And now here, when the block is at x equal negative s, it's to the left of equilibrium. So think about that for a moment. What is your free body diagram going to look like then? Well, it's still going to have a normal force. It's still going to have weight. But now the block is to the left of equilibrium, so that means the restoring force will be directed to the right. So K prime S will be the magnitude of that force there. Okay, and then we're asked to find the time, right? What time is it when x equal negative s? So let's think about how we're going to handle that. How can we solve for the time? Well, I would probably go back to the position function again. And then you think about, like, okay, they're asking me to solve for t when x equal negative s. Could I do that? So let's start a new page for that. And I'll go back to my position function. So x equal a cosine omega t plus phi. This is just my general function here. And now I'm going to apply it for when x equal negative s. So that means negative s in place of x, right? The amplitude's given as 2s. That's a constant, right? So that doesn't change as time goes on. Cosine. Now remember, we solved for omega. We did it. So that's cool. I can just sub right in for that. So that's root k prime over 3m. I know that. Times t plus, and now I know my phase constant. My phase constant in arc cosine 1/4. Great. So look, everything in here is something that's known except for my time, right? Everything is known except for time. So all I have to do is a little bit of algebra here. Y'all can handle that algebra. I'm going to say here algebra intermission. As usual, all the details are found in the written solution. And then when I solve for time, my final expression here is time is equal to root 3m over k prime times a quantity arc cosine negative 1/2 minus 1/4. Okay. Let's see what else we got here. So that was part D. And part E asks us, what is the speed of the block at that moment? Okay, so this was part D, and now we're into part E. Part E asks us for the speed of the block at that moment. Well, I know that I have my velocity equation. Let's go back. Remember that we when we first wrote the position equation, we also wrote the velocity equation here. So now finally someone's asking me about velocity. Negative a omega sine omega t plus phi. The question asks for speed. I don't know if you noticed that. The question asks for speed. So we're just really interested then in the magnitude of this. So the speed is just going to be, you could think, the magnitude of the velocity, which we usually just write as a v without the hat, right? And then I can write that as a omega sine omega t plus, and I know I want the absolute value of that. Sine, of course, can produce a positive or negative, right? So I know I'm going to want the absolute value of that thing. Great. So I'm interested in the velocity at this time right here, the time that I just found. So that's actually the time that I want to substitute into the velocity equation. So if I solve for velocity here, what will I get? My A amplitude, remember, is equal to 2s. Omega is equal to root k prime over 3m times sine. So I'm just sticking with this equation here, right? I've expressed the A, I've expressed the omega. Now I'm expressing the sine function. So this is going to be sine of omega t, so that's root k prime over 3m t plus the phase shift, which is arc cosine of 1/4. Okay, so this is my expression. What I have still to do here is to take the time that I found in part D and substitute it in for this time right here. And that'll be my last move to do that substitution. And but the physics part really is done at this point. And the written solutions have all the steps for subbing in the time and what your final expression will look like.